Okay, so yeah, I'm here to talk about a quantum cat game that I've been working on. So a little bit about me. I'm Sarah Marshall. I'm a software engineer at Microsoft Quantum. I work on Q#. That's my day job. Work on mostly the Q# compiler and sort of like Q# language design and that sort of stuff. This game is totally unrelated to my job. It's something that I've been doing in my spare time just for fun. And yeah, so a little bit overview of the talk. I'm going to start with a little bit of background, just a couple other quantum games that we knew about before we started this game, and sort of just like describe them and describe how our game is different from them. Not like a comprehensive survey of all quantum games, just like the two that we knew about before we started. And then after that, I'll talk about the game, which is called Superposition. Then we'll do a live demo. And after that, I'll talk about sort of the technical details behind the scenes of how superposition works. So that'll include the quantum simulator that we use to simulate the puzzles as you play them. And then a little bit about how we deal with the kind of complex quantum stuff that we need to describe in order to have puzzles in the game. We've sort of developed our own system to handle the complexity, and I'll get into that at the end. And yeah, sort of my goals for this talk are well, mostly just to show off a fun quantum cat game. Hopefully people will be into that. Number two is just sort of to hopefully provide some new ways of thinking about quantum computing, because while our game is designed to like be an accurate simulation of a quantum computer, so in that sense it's not really doing anything new compared to existing simulators. But for the game, we had to sort of think about how a simulator works in a different way, because our game has specific needs that a general purpose simulator doesn't have. So we sort of have to come up with our own ways of thinking about that. So it's just a different perspective. So yeah, here's the first quantum game that I sort of found out about was this quantum game with photons. It's just like an online web game. You sort of shoot a laser. You shoot a single photon from a laser, and it just sort of moves around the level. And you have to like set up mirrors and beam splitters and different things around the level to sort of get the photon into the detector in the right state, or maybe into multiple detectors. You have to avoid obstacles like this cute rock with eyes, which I think is amazing. But yeah, it's pretty simple. Like it's simple in a good way. Like it's good to like get into quantum mechanics, but it's not like a quantum computer simulation per se. It doesn't really have qubits. It just has this quantum photon, but it doesn't really have like gates and stuff. Then there is Hello Quantum, which the video is not showing. I think here we go. Yeah, so this is like a mobile game, phone game. You sort of have like a 2-qubit system, and it's sort of visualized as this 2-dimensional grid, and you apply gates to it, and it moves things around in different ways. Yeah, but it's also sort of has that vibe of like it's simple, it's easy to get into, but it's still like limited to 2-qubit systems, and it's sort of very abstract. It's sort of just this like 2-dimensional cyber grid. And we sort of wanted to make a game that was sort of like similar to a 2-dimensional like action adventure game, sort of less abstract, having visuals, having cats walking around, having qubits that you can pick up and lasers you can fire and stuff. So we wanted to sort of have a friendlier shell around the same sort of quantum mechanics, quantum computer simulation. Yeah. So one of our goals was to try to teach quantum mechanics in the form of a video game. And to do that, we wanted to be able to have our game puzzles support actual quantum algorithms. Like we wanted to be able to apply gates while you play the level. And so solving a puzzle would be like constructing a quantum circuit on the fly. And we wanted to be able to like teach circuit identities, teach how algorithms work, and sort of also visualize that in an intuitive way. So we wanted to be able to visualize like complex superposition states where like lots of things are going on. Things are in multiple places at once. Things are on and off at the same time. Cats are alive and dead at the same time. We wanted to visualize this in a way that makes sense and is intuitive. And last but not least, we wanted to just make a game about a cat because cats are cute. Yeah. So I started this game with Rory Soifer. This was sort of it's a two-person, a few more people involved, but mainly two-person project that we started in summer 2019. So it's almost a year old. Not quite. I think in a couple months it'll be a year old. We haven't been working on it continuously. It's just sort of when we have time in our spare time we work on it, which is unfortunately not as often as I would like.
Sarah, just a quick question. Does the cat have a name? Chad is asking.
Does the cat have a name? I think it's undecided. I kind of want to call
That's a funny name.
I kind of want to call him Erwin. It's a name after Schrödinger's first name, because I feel like Schrödinger's cat should like look like Schrödinger and be like Schrödinger in some weird way, but we haven't really decided what to call the cat.
Would be a good thing to file an issue on the repo for, yeah?
Yeah, you can make a future request.
I like Rohit, we had the same idea at the same time. All right, sorry for the interruption.
Yeah, no worries. Yeah, feel free to interrupt and ask questions. That's totally fine. So the premise of the game is you play as Schrödinger's cat. You're inside the quantum box in the thought experiment. So for those who aren't familiar, the thought experiment is that Schrödinger has a cat inside of a box that's sealed out from the outside world. You can't observe anything inside of it. And you have this quantum device in it that, this is where it gets sort of morbid, but the quantum device will like kill or not kill the cat, or release a poison depending on a quantum event happening, and that quantum event happens probabilistically. So the thought experiment is like, what does it mean to have a probabilistic event inside of a box? Like, is the cat alive and dead at the same time? Like, what does that mean? And Schrödinger himself sort of used it as a way to say, like, this is obviously not real. Like, quantum mechanics couldn't possibly work like this. But yeah. So we sort of wanted to take this and just like run with it and say that, yeah, you know what if this does actually happen? Like, what if you actually can be alive and dead at the same time? And that's sort of, you play as Schrödinger's cat and you actually can be alive and dead. So that's sort of what our game does. Another important part is that everything you do in the game should be a quantum operation. So as you're playing the game, as you're moving around, picking up things, clicking on things, you're applying quantum gates to the quantum state. And this is important because we wanted to be able to teach real quantum mechanics, real quantum computing, and so we needed to have a simulator that does that. Oh, sorry, I think my slides got messed up. Okay, yeah, so basically the idea is that everything sort of looks normal at first. Like the game supports just like a totally normal, there's no superposition at first. You just have a cat. You can have these ball things are how we represent qubits. So it's basically like a qubit in ball form that you can pick up and move around. And you can just like fire lasers at them. And it looks like pretty standard until you start adding superposition, and then things get really weird because you can be in multiple places at once. You can be alive and dead at the same time. You can have this qubit that's like on and off at the same time and also in different places at the same time. And yeah, so it gets pretty intense, but we try to visualize it in a way that sort of makes sense. And yeah, so we have a quantum simulator that the game uses for all of the puzzles. It's a custom quantum simulator that we wrote for the game, but it's designed to be like accurate, like mathematically accurate. So each level has a quantum state, and like I mentioned, like you're applying gates to it. So we wanted to make sure that everything you do in the game is we're not teaching incorrect things. So we need to have an accurate quantum simulator. Every action is a unitary quantum operation. And just some intuition in case you don't know what unitary means. For an operation to be unitary, it basically has to preserve, everything you do has to preserve quantum information and can always be reversible. So there's a couple more math things to this definition, but this is just sort of like the basic intuition is that every action in the game has to be reversible because quantum information can't be destroyed. And it's sort of just like every quantum gate in a real quantum circuit has to be reversible. So an example of that is a laser. If you shoot a laser at the cat will die. But it's okay because if you shoot the laser again, the cat will come back to life. So the laser itself is a reversible operation. And in fact, it's just the X gate. So when you apply the laser, when you shoot the laser, you're actually just applying the X gate to the cat's alive and dead state, which is a qubit. So the cat being alive or dead is represented by a qubit. And so X gate will switch the state to dead. X gate again will switch it back to alive. So in theory, this means that you can never get yourself into a state that you can't get out of. So theoretically, everything's reversible. You should always be able to like undo what you did if you get yourself into a dead end. But because our levels get pretty complicated, we still have a reset button because you can sort of get things into an arbitrarily complex state that's very hard to reverse. So you can still reset the levels and try again. Another interesting thing about unitarity is that it makes some actions impossible, and we need them to be impossible to have a consistent quantum simulation. So for example, if you have the cat in two different places at the same time, and the top cat is next to a wall and the bottom cat is not next to a wall, you actually can't move either cat up because when you press like the up key, it moves all the cats at the same time. And so you can't get into a situation where like you move the bottom cat up, but the top cat gets stuck against the wall. Because then the bottom cat could move up, the top cat is stuck, and then you would sort of overlap. The bottom cat would move up to the top cat and they'd be on the same place, and then you couldn't reverse that. You would sort of lose the information that they were separate, and they would just, it wouldn't be a unitary operation. So we just sort of prevent the player from doing these things, and it sort of makes the puzzles more interesting, as well as being accurate to what quantum computing is. So you might be wondering about like measurement. Measurement's not really a unitary operation. It does destroy information. It sort of collapses the state. So we don't have that. We just sort of took a design decision and said that we're not going to support measurement. It's sort of just simpler just to have everything be unitary. And yeah, and Yeah.
Sorry. So there's a question in chat. Is there decoherence built into the game? And I'm guessing if there isn't measurement, there might not be decoherence either.
By decoherence, do you mean like noise, or?
Yeah, or like a time limit for. So Rohit asked, like, is there like a time limit or decoherence for like how long things will stay entangled or correlated or something like that?
I see. Yeah. No, there isn't. Yeah. So the state will last indefinitely. There's no noise. It's just sort of always a pure quantum state that is deterministic and will last forever. Yeah. So no time limit.
The best way to the best and easiest way to model this.
Yeah, it's like we could probably add that'd be weird if we added decoherence time and noise. That'd be an interesting thing we can consider adding, but for now, yeah, we just keep it simple, pure quantum states, no noise, no measurement.
I see that as like an Iron Man or a hard mode for the game. Is like now you have a time limit for how long you can make the decisions.
Yeah, that would actually be very interesting. Okay, so the goal for every level is that the door starts out locked, and you want to get through the door because the door is how you beat the level. You have to unlock the door by getting a qubit into a certain state and putting it next to the door. So for here, like this qubit is just like 0 or 1, you just put it in the 1 state, and it opens the door. But we also have more complicated states, like we can have multiple qubit registers. So you might have like a cue ball containing 4 qubits, and they have to like be in a certain state to open the door. So it's like a door code in that sense. And yeah, so that's sort of the overarching goal for all levels is to get the qubits into the right state to open the door. And yeah, so these cue balls are just a representation of a qubit that you can pick up and move around. They support single qubit cue balls. There's also multiple qubit cue balls. So on the middle is a 4 qubit cue ball where the left 2 qubits are on, the right 2 qubits are off. For the right cue ball, it's all 4 qubits are on. But they can be in any state, any combination of on and off, and also in a superposition of on and off. So yeah, that's sort of the background. And now I wanted to do a demo of the game. Let's see if I can load it up. Okay. Is this working, Sarah?
Yep, you're good. Okay,
cool. So here's the game. This is the very first level. You start out in a completely empty room. Is teaching you that you can open the door with the cue ball. Here's a laser. So this is applying the X gate to the cue ball, and so the cue ball starts in the off state. You fire the laser and it turns it on, and then you can bring it over to the door. If it was in the off state, it just wouldn't do anything. So lasers can also be controlled gates. So this is a C0 gate. It's a controlled X gate. We put this cue ball in the 1 state here, it turns the laser on, and then we can fire it at this cue ball. Then we need both cue balls to open the door. Okay, so now we have superposition. So this cue ball is in 2 places at once, and we show this as being like different colored versions of the cue ball. So the red color version is over here, and the blue color is, yeah. They're things that have the same color are sort of part of the same universe, and they're sort of correlated in that sense. So we can show entanglement via colors as well. So an example is we put the cue ball on here, and now this laser, which is a controlled X gate, is powered by this cue ball, but the cue ball is only there, it's only half there. So now this laser is powered in the red universe, but in the blue universe, it's not powered. So if I shoot this cue ball, it'll only negate, like it'll only apply an X gate to half of this cue ball. I need to remember how to solve this level. So I think that if I just swap those, and then I can apply, yeah. So basically what happened was I did a C naught based on this control, and I did a C naught based on this control, and that is both of the controls. So it sort of has the total effect of just applying an X gate to the entire cue ball over here. And now I can open the door. This is an entanglement level. So these doors, I need to be able to get the cat through both of these doors at the same time. But the doors are only half open. So this door is open in this door looks red because it's closed in the red universe and open in the blue universe because this blue cue ball is opening it. And this door has the opposite. So this door is open in the red universe and closed in the blue universe. So what I can do, since this cue ball is powering this laser in the red universe, I can fire the laser at the cat. And because the cat is dead in the red universe, he can't move. So when I move, I'm only moving the alive cat. And I can move over here and fire the laser again to reverse that. And now I have two cats. And they're also entangled with these cue balls. So this cat is entangled with this cue ball, this cat is entangled with this cue ball, which means that I can just walk through the other door at the same time. And yeah, so some more stuff you can do with entanglement. I can pick up this cue ball. I only pick up half of it because I'm only alive in the red universe. And actually don't want to do. I want to move this cue ball. I solved this level before I started the talk today, but sometimes I can still get confused because it's tricky. So I want to entangle myself with this cue ball. Oh, right, and then here's an uncontrolled laser up here. I forgot about this. So I can just fire this, and this will toggle this cue ball. And now this cue ball is white. It's in the on state, so I can just open this door. This door's only half open, but I'm entangled with this cue ball, so I can walk through it. And I can pick up this half of that cue ball. And then I have to do this again with the other blue universe. So I actually want to change this.
So other than entanglement, what other kinds of operations are kind of going on in the back, like behind the scenes here?
Behind the scenes, so every time I move, I'm actually applying a gate to the cat's position. So when I move to the left, it's actually applying like a translation gate to the cat's quantum position and moving it to the left, to the left. And this translation gate is a controlled gate based on the cat being alive. So it only will apply the gate if the cat is alive in that universe, which is why it doesn't translate the cat when the cat is dead. And that's sort of how I'm able to like split the cat like this.
Awesome. That's so cool. Chat really loves both the sloshy gel effect. The cats are super cute. People were excited to see what the entanglement stuff looked like. Yeah.
Yeah, cool. Yeah, so I need to get myself, right, okay, so I need to get this blue cue ball, turn it on here. I'm gonna get this cue ball, and now, yeah, I'll just recombine myself. I will merge my cats. And now I have this entire cue ball, which is entirely on. And now I can go through the door. Yeah, so now we have these cue balls, which have like 4 qubits packed into 1 cue ball. And we have to like match the code. So this cue ball will open this lock. And this lock just needs this one. But they have to match. So if I like swap these two, the door won't open. They're like lock codes for the door. And then do you want, I think that this one will also open this one. This one's not picky. This one only has 1 bar, so it'll work with anything that has a white bar on the rightmost qubit. Then use something that has this one, yeah. Here's an example. Okay, so lasers get kind of interesting when they're controlled by a cue ball with 4 qubits. So now this laser will actually fire 4 different beams. It's only firing 2 now because this cue ball is only on in the left 2 qubits. So it's sort of controlled based on this, so it's only firing the left 2 beams. And that'll sort of apply the X gate to the left 2 qubits of this cue ball, which is why these are being toggled on and off. So I need to actually just do the rightmost qubit to make this all on, and that will power that. And now I have this one. I'll do that. These are magic cue ball repelling grates. You cannot carry the cue ball. We should probably come up with a better graphic for that. But yeah, basically the idea is that the cat can walk through them, cue balls can't. And this will make sense in the next level. There's a reason why we have this. And it's because we can actually implement a circuit identity. So you might have heard of.
This is really cool.
See where this is going. If you're familiar with the swap gate, you might know that it can be decomposed into 3 C-naughts. You have a C-naught, C-naught controlled from like A to B, then C-naught from B to A, and then C-naught from A to B again. And that is an identity for swap. It's equivalent to swap. The lasers are controlled X gates. So if I take this cue ball and put it in the path of this laser, that's a C-naught on this one. And then go over here and do it with here. That's a C-naught from this one to this one. And then finally, to complete the circuit, I do the last C-naught from this one to this one. And now I have swapped their states. So this cue ball used to be over here, this cue ball used to be over there. I couldn't carry them across because of the magic rates. But now because of my triple C-naught swap, I have swapped their states, and now I can open the door. And yeah, so
oh, no.
yes, our game supports the quantum Fourier transform, which is visualized by Mr. Fourier himself. He has appeared in our game.
Who trapped him in the box is my question.
That'll be part of the plot of the game, perhaps. Yeah, for a single qubit state, the Fourier transform is just sort of the same as an H gate. So we have this cue ball that's in a superposition of on and off. It's in the plus state. So if we apply Fourier, which just does an H gate, we sort of go from plus state back to, or sorry, it was in the minus state. I think it was in, yeah, it was in the minus state. Because H will map minus to 1. So now we have cue ball in the 1 state, and now we're going to store. And yeah, some more. I think I might end the demo here to avoid showing too much of the game. This is just a taste. We have a way to change the phase, and we sort of visualize the phase with this compass in the bottom. We're not sure if this is the best way to visualize it, just sort of what we settled on for now, because it's sort of good enough. The phase is represented by which direction the arrow is pointing, or this bar is pointing. And the phase can depend on the universe. So in the red universe, the phase is pointing to the right. In the blue universe, the phase is pointing to the left. That sort of means that I think this will map to like the red is the phase 1 and the blue is the phase -1, which means that we have red is off. So that's 0, ket 0 plus minus ket 1. So it's 0 minus 1, and that will be the minus state.
It looks like you have some diagnostics up in the top left. Is that part of the game, or is that part of debugging?
Yeah, we're not sure what we want to do with this. Basically, the idea is that if I go back a couple levels, yeah, the idea is that like sometimes, like, so we try to make our visualization as sort of intuitive as possible, but sometimes it's hard to see what's going on if there's a lot of superposition and weird stuff involved. And so we sort of have this as a way to like just show you exactly what's going on, to show you the numbers and the raw data. And I'm not sure if you want to have this in the final game. It might not be necessary as long as our visualization is good enough, but yeah, so it's sort of like a debug thing right now, but maybe something similar could be an option if you want to look into the quantum state. But this is basically showing all of our the universes are the rows. So we have the red universe at the top row, the blue universe at the bottom row. They have their probability amplitudes here, and this will show like the states of all the objects in the game. So this is the cat's alive dead state, and this is like the cue ball. This is the other cue ball.
Maybe you get like oracle tokens, and those are like the help, and you can redeem them to turn on the diagnostics for a little bit.
Yeah, maybe that might work.
Sweet. Well, this is an awesome demo. Like Victoria says, this is amazing. I want to play it.
Yeah. So you can actually play it yourself if you want to. Let's see if I can. I'll go back to Firefox. So in the repository, which should have a link to in the chat. Right now, I should add a README, but so it's a little hard to find things. But in the releases, you can actually download this demo. Right now, it unfortunately works in Windows, but we should be able to have Mac and Linux support now. They're just we should be able to have Mac and Linux support, but they're not available now. So it only works on Windows. But yeah, you can download it if you have a Windows computer.
Would that be a good thing people could help out with?
Yes.
As like a help wanted issue?
Yes. I should actually make an issue for Mac and Linux support. Yeah.
I'd like somebody to open an issue for the name the protagonist. Good job, chat.
That's amazing. Thank you. Yeah. So, okay. Let's see. So I think that was the demo. There's more levels. There's yeah, there's only a taste of the beginning of the game, so you can try the demo yourself and try to see if you can beat all the levels. So yeah, let's sort of talk about how we do all this. So how do we create the state and let you manipulate the state in this way and have it all sort of work as like a real quantum simulation? And to do this, like at the very start, we had to decide what should be part of the quantum state and what shouldn't be part of the quantum state, because if absolutely everything in the game state was part of the quantum state, it would be sort of confusing. For example, if we made like the exact pixel position of the cat is part of the game state, because we have to know where the cat is to draw the cat at the exact pixel position that it is. But if every pixel was like a different quantum position, it would get very hard to line things up correctly and to apply gates to things, because they would just like be missing other things by pixels, and it would be sort of confusing. So we made this simplification that we sort of discretize the positions into different cells. So cells are just these big blocks. Anywhere in the cell is, if you're anywhere in the cell, you're just in the cell. It doesn't matter where you are. It can be in any corner, anywhere in the cell is the same quantum cell as far as the quantum state is concerned. The graphical pixel position is just sort of for appearance purposes. It doesn't affect the quantum state. It's just to make the animation smooth. Speaking of animations, we also have doors that animate. We have other animations as well, and we don't want to make those part of the quantum state because, like, there's not really a reason to put them there. They would just sort of make things more complicated, and we don't want to make any quantum operations depend on like which animation something is in at the moment, or even like which animation frame. Like, we don't want the animation frames to affect how gates work. They should just be just sort of a visual effect. So yeah, we had to make these decisions that we don't want exact pixel position and animation timers to be part of the quantum state. But we have this problem because those things can still depend on the quantum state. For example, the cat, can be in two places at once within the same cell, because like the cat could have been, you could apply like a C0 laser to the cat to kill half of the cat, and then you move the alive cat away, and now you've sort of split. So you're in the same cell, but you're at different pixels. So we still need some way to track this information with the universe. Like with each superposition state, each basis state that you're in, we need to be able to track this other additional state that's not officially part of the quantum state. So we sort of already have this sort of association between basis states like alive and dead and their probability amplitudes. So you can think of a quantum state as being a mapping from all the basis states to their amplitudes. And it's actually not too hard to just like associate a little bit of extra information with that. So we can say, instead of just saying like, what's the probability amplitude of alive, what's the probability amplitude of dead, we can say like, okay, we're also going to associate the pixel position with the alive basis state, and also the pixel position with the dead basis state, and they could be different because the cat could be in different places depending on whether it's alive or dead. So you can sort of just think of it as having this mapping or dictionary, and we're just adding more fields to what the basis states map to. So we just add a little bit of more, make it a tuple or make it a class, some kind of object, and we just store this metadata for all the stuff that we want to include that we don't want to make part of the quantum state. And yeah, so this sort of combination of basis state, probability amplitude, and metadata, all that combined, we call a universe. And then that sort of natural thing to say is that, well, if you have a bunch of universes to describe your quantum state, now it's the multiverse. And so the entire game sort of takes place in a multiverse that's sort of divided into different universes. This is just our terminology. So pixel position is metadata, but we still have cell position. So the discretized cells are part of the quantum state. So we can represent these as qubits because it's more than a qubit. Like a qubit is just on or off. A cell position can be any cell like on the map. So there's a lot more possible states for the position of the cat than just like on or off. That's just a two-state. A qubit is just a two-state object. Need more states than that. So in general, that's just a qubit, where the D is just like the, I don't know what the D stands for, just like the D is the number of possible states that a quantum thing could be in. And in the game code, we just say like, well, the alive qubit is just, we just allocate this quantum state with the initial value of true. And that sort of says that this state is of type Boolean. And then we just do the same thing with the position. We just say, well, the initial value is a vector, a two-dimensional vector. So like the x position will be 2 and the y position will be 0. And then we just have this quantum object in our quantum state that just is a vector. And so our quantum simulator has to support arbitrary types. It's not just a qubit simulator, it's a qubit simulator, and we sort of represent that as just being any type you want. So it's a generic type in the code. And then, yeah, so there are a lot of cells. Like there are a lot of possible positions that you could be in. So that has some implications. Like how do you represent that? How do you represent like the superposition of multiple cells? Because the traditional way for a quantum simulator to do this is to use a state vector or like a wave function. Where each cell, each component in the vector corresponds to a basis state. So this grows like exponentially with the number of qubits. So if you have a 2-qubit system, you need a 4-component vector to represent all of the possible basis states, 0, 0, 0, 1, 1, 0, and 1, 1. And so this doesn't scale super well because we want to have cats be like in any possible position on the board, which like based on this screenshot is about 84 possible positions, ignoring walls. And so that's like, those are our basis states. So if you want to have a cat and a cue ball in our quantum state, you got 84 positions for the cat, two possible states for the cat being alive or dead, and you multiply them. You also multiply the same for the cue ball because the cue ball can be in any position as well, and it can also be on or off. And you end up with this state vector that has like 28,000 components in it, which is like, that's not like impossible for a computer to deal with. It's not that large for a computer, but it's a bit excessive for what is just a cat and a cue ball. Like it's very inefficient. And it gets worse because if you want to have like 4 cue balls, which we do have levels with 4 cue balls, so you just take this, you add 3 more cue balls, which doesn't seem that bad. So you take that last number, and then you have 84 times 2 for each cue ball, because each cue ball has 84 possible positions times 2 states on or off. And you have to do that 3 more times, and you end up with this state vector that has over 100 billion components in it for a cat and 4 cue balls. So this is, you end up with this giant state vector, and it's not an efficient way to simulate things. So we don't do this. This is, yeah, this would not be good. But there's like an observation you can make, which is that most components of the vector actually end up being 0. So for this screenshot, for example, there's like a lot of things going on in the screenshot. There's a cat in like 2 different places, a cue ball in 2 different places, cat's alive and dead. there's like a decent amount of superposition happening here, but there's not anywhere close to the maximum amount of superposition happening. There's only a handful of cells are occupied, only about like 5 cells compared to all of the possible cells. It's actually fairly empty. And this means that most of the components in the state vector would be 0. There's like a 0% probability of measuring the cat in most of these cells. They're just not there. So this lets us make a simplifying optimization. And instead of having the entire vector, we just have a sparse vector. We only store things that have non-zero amplitudes. And I think there are different ways to represent a sparse vector. You can use that like a map or a hash map or something like that. For us, we just use a list. A list is simple and it sort of works for our purposes. We don't have very large lists, so we just use a list and we put the universe in the list. So the universe will have its probability amplitude and basis state and metadata associated with it, and we just put it all on the list. And this is sort of an equivalent representation to the full state vector. Then we want to do stuff to the state. So we want to apply operations to it. And we also run into this similar problem, which is that normally traditional simulators sort of do matrix vector multiplication because they represent state as a vector and they represent operations as matrices, and multiplying them together is how you apply operations, but we have a sparse vector. And so we sort of could do matrix vector multiplication, but it would still involve like iterating over more things than we would like. Like we wouldn't be able to just iterate over the 2 universes in our 2 universe list. We'd have to iterate over additional things as well to sort of apply these matrices to it. And so we want to find a better way to do that. So we don't use matrices for operations. We just say a unitary operation is some combination of a function that takes in a universe and returns 1 or more universes. And then we also have an adjoint. So every operation is reversible, so it has to define like what's the opposite of it, and that's what the adjoint is. But fundamentally, for us, an operation is a function from a universe to 1 or more different universes. And this is like, this is sort of how that works. And it's sort of simple once you like understand it. It's like an X gate. For example, if you find X gate to ket 0, you get a list, or you turn ket 0 into ket 1. So for us, that's a list with 1 item in it. We say you put in 0 into the X gate and you get out a list containing just 1. It has flipped the bit. And same with 1. 1 maps to 0. And then HK is a little different because HK creates superposition in the computational basis state. So it'll actually map 0 to a list of 2 items. It'll map it to 1 over root 2 ket 0 and 1 over root 2 ket 1. And for 1, it'll do the same, except the second component will be minus because it's it maps 1 to the minus state. Yeah, so instead of having operations be matrices, we just have them be functions from universes to 1 or more universes. And if you're not creating superposition, you're just returning one universe, a list with 1 item in it. But if you do create superposition, you can just return more than 1 universe. And that's sort of how we do that.
This feels, so like kind of what you were just showing feels a little bit like truth tables. Is that maybe a fair way to describe it? Or like these functions kind of just give the mappings between your input state and particular output states in 1 or more universes?
Yeah, well, I guess when I think of a truth table, I think of like a classical classical Boolean logic truth table, where like everything has one output. So I guess the difference for us would be that you have more than one output. You can map something to more than one output. But yeah, and I mean in that sense it is similar. Yeah, it's like the quantum version of that, I guess.
Cool. Thanks.
Yeah. So an example of applying a gate to a multiverse that already has two universes in it. So we might be in a superposition of 0 and 1, and this technically should be normalized. I'm not going to write the probability amplitudes just to make it simpler, but there should be like 1 over root 2s here, but I'm just going to write the states without the coefficients. So you might have a blue universe where some state is in the 0 state, and a red universe where some state is in the 1 state. And if you want to apply an H gate to it, you will map over all the universes in the multiverse and apply that gate to each universe. So the H gate applied to the blue universe will produce 0 and 1. So it'll split the universe into two universes like we showed before. And for the 1 state, it'll do the same. We'll split the red universe into universes where the 1 state has a minus phase. And when it makes these copies, like the blue universes come from the original blue universe, and the red universes come from the original red universe. So it'll copy metadata with that. So if the cat is in some pixel position in the blue universe, when the operation is applied, it'll just copy over all that metadata along with it, and it'll copy it and split it into those two universes. But the state isn't fully simplified, so we actually have to do a pass to sort of add up like terms and combine things and sort of simplify them, because this will simplify to just 0 state, because the 1 and minus 1 will cancel out. But that's sort of it. So yeah, so we apply each operation on a per universe case, like a per universe case. So we will just map over the list of universes to apply each gate, and then after that we'll end up with too many universes because it's not going to be simplified, and then we do a simplifying pass over that. And this is sort of equivalent to matrix vector multiplication. It's just a different way to think about it. And it works better for our needs because it doesn't require constructing or iterating over large vectors or matrices.
Yeah, it seems to be a lot of savings for the actual modeling, so you don't have to keep track of all the zeros because they're not doing anything anyway.
Yeah, exactly. So I said earlier that lasers were X gates, and this is true, but it's also not true. Like they're more than just an X gate. Because they sort of, if you fire a laser and it hits a cue ball, like it could only hit that cue ball in one of the universes. So in this screenshot, this qubit inside the cue ball is in 2 different places. So the red cue ball and the blue cue ball are the same qubit, but they have different locations. And we only want the laser to affect cue balls in its path. So it should apply the X gate to the red cue ball, but not the blue cue ball, even though they have the same qubit, same underlying qubit. So lasers are actually sort of a complicated like system of control gates where they will only apply the X gate controlled on the cue ball being in a certain position, being in the path of the laser, and also controlled on it being like the first cue ball in that path. Because if there's another cue ball after the red one in the red universe, it won't hit that. Like the laser will stop at the first thing. So this ends up being sort of a really complicated gate that we have to apply beyond just a simple X gate. And so we need some way to sort of represent this in a way that's easy to write. Sort of like, I just want to be able to describe at a high level what I want the gate to do and just have them sort of the math work out for us. And we wanted to guarantee that the gates are unitary, because if we make a mistake and we end up with a non-unitary gate, that'll break the game, and we don't want that. So we started to develop this system for dealing with the stuff where so lasers are like a two-step thing. So first we find all the things that laser hits. So we call this beam hits function, given the multiverse, and I forget what entity is, but basically beam hits is returning a list of all the qubits that the path will hit, that the laser will hit in its path. But that depends on the universe, because the list of qubits that it hits in the red universe is a list of one thing. The list of qubits that it hits in the blue universe is an empty list, doesn't hit anything in the blue universe. So we sort of conceptualize this. Our abstraction for this is something called a QXPR, which is just a quantum expression. It's basically any expression whose value depends on what universe you're in. So we have this list of qubits, but it's inside of this QXPR, so it has no value until you tell it what universe it's in. So the expression itself is sort of in a superposition. So our code, we have to the superposition expands into our code to make our code easier to write. And then we take the gate, which will just be like an X gate or a controlled X gate. We turn it into a multi-version of that. So the base gate will just apply to one qubit, but the laser could hit multiple things if they're on the same cell. So we turn the gate into a gate that takes in a list of qubits that are just one qubit. We tell it to take in, instead of a list of qubits, we want to take in a quantum expression of a list of qubits, because a list of qubits itself depends on what universe the beam is in. And finally, we give it this quantum expression we prepared earlier, which has the list of qubits. And this will automatically know which qubits to apply based on the universe. It'll sort of automatically do the per universe iteration through the multiverse to find out which qubits to hit in this universe, which qubits to hit in that universe. It'll sort of do all this automatically and in a way that's unitary. And it'll check for unitarity. If it's not unitary, for example, if you control on something you're targeting, it'll complain. And then finally, we have this unitary thing that doesn't do anything yet. We give it to the multiverse and say, apply this unitary operation. And that will do the thing I talked about earlier, which is mapping over all the universes, calling the unitary apply function on each universe, and then doing the simplification, all that stuff. It'll just sort of do that for us. Yeah, so this is sort of how we build up these complex quantum gates in a relatively simple way.
Yeah, that syntax looks like this entire construction looks really looks like it would make it much easier to express what's going on in the game.
Yeah. The language we use for the game is Scala, and I feel like Scala has sort of helped us a lot in building really nice APIs for our quantum simulator, because Scala lets you do cool things with syntax. You can make gates act like functions and sort of work with QXPRs in a cool way. So yeah, there's more that I'm not showing here. That we have some different ways of working with quantum expressions that really sort of simplify things and bring it to a higher level of abstraction, which is useful for our game, which is very abstract.
A good advertisement for people to go check out the source.
Yeah, the source is on GitHub. Yeah. But even this is can sort of get out of hand, because this is a nice syntax, but when you're applying even more complicated stuff, it can sort of get tricky to keep track of all the QXPRs everywhere. So we need some way to describe this at an even higher level. That's sort of something we've encountered, was we needed to build an even higher abstraction, because we end up with these really complex quantum states, and we want to do complex operations on them, and we want to sort of think of them without having to worry about all the different universes. We just want to think about them, like pretend they're classical, in the sense like just say, I have this list of list, but you can say like, I want this door to be open if there's a cue ball in the one state, and I just want them to write door is open if the cell has a cue ball in the one state. And I don't want to worry about, does it have a cue ball in the one state in this universe or that universe? I just want to say what I mean, assuming that there's one universe, and have it just automatically work for all universes. Another thing we needed was we wanted to be able to wanted to make puzzles, make game levels without editing the code. So we wanted to be able to do it in a graphical editor, and just write in these quantum scripts into the editor without having to touch the game code itself. We ended up developing a quantum scripting language, sort of a quantum DSL for the game. We wanted to have like an English-like syntax, so it sort of reads like English approximately. Want to be able to express high-level concepts very concisely, sort of like I'm talking about, where you can pretend that something is a classical state when it's actually a quantum state, and I just wanted to have it automatically figure that out. I don't have to talk about different universes. It's very specialized for our game scripting needs. Like, this is not a general quantum programming language. It's not a competitor to Q#. It is very much specifically for our game and sort of our needs in scripting, writing quantum scripts for our puzzles. The scripts end up being very short. Like, they're just short descriptions or commands for like gates we want to apply or states we want to check. So one of the simplest examples is just a script that applies the H gate to qubit number 16. This is pretty simple, not that impressive, but it sort of shows our syntax. They sort of format things like a sentence, it ends with a period. We use English prepositions and that sort of stuff. We can also do more complicated things. We can say, for example, if you have a door that you only want to be open if you have two cue balls in the one state next to it. So you want, like, this door has to be powered by or unlocked by two cue balls. You can say, well, the door's open state is this expression, which is the Boolean and of, is there an active, so active cell just means, is there a cue ball in this cell that's on? So if there's a cue ball, if there's an active cell for, if 9-2 is an active cell and 10-2 is an active cell, then this will evaluate to true and the door will open, but it'll only open in the universe where this is true. This expression depends on the universe implicitly. We can also do more complicated gates. So for example, if you want to make a level, make a puzzle where a cue ball sort of starts in a superposition of positions. So we want the cue ball to start in two different places at once. You can sort of initialize the level with this script and say, I want to apply the translate gate to the cue ball's position. So qcell is a function that returns the position qdit for the entity ID 16. And we'll translate that by -1 in the x direction and 0 in the y direction, which just means move it left by 1. But we only want to translate it if the qubit is on. So this script will turn into a controlled translate based on the qubit being on. And we can go even more complicated things, do even more complicated things. We can define a quantum Fourier transform gate and sort of apply that to whatever cue ball happens to be in the cell. So we can say, like, for the cell 9-5, find a cue ball in it and apply QFT to it. And then we can do this phase gate. We can repeat it, sort of like a loop, it's a loop that depends on the number of times you loop depends on the quantum state in a cell. So yeah, that's pretty cool. And then you just reverse it. So you sort of apply the adjoint of Q of t to sort of undo it, undo the original Q of t. So you sort of conjugate it with that, with the Q of t. So yeah.
So this is like a bonus talk. You get a quantum game stuff and a quantum scripting language.
Yeah. So yeah, I sort of mentioned how our language works is that every expression is quantum. The universe, the different universes are sort of implicit. So like this saying like, this is a Boolean expression, Boolean function. It takes in the cell number x equals 9, y equals 2, and it'll return true if there's a cue ball in the one state. But it's just sort of, this expression depends on the universe. It just sort of automatically figures that out. You can sort of think of it as like what's happening behind the scenes is you're passing in the universe, passing in a particular universe into this function, and it'll return either true or false. But because we have to do this so often, like because all of our quantum puzzles depend on quantum state, and that quantum state is sort of inherently could be different in different universes. So having to pass in universe all these things wouldn't, like, it's sort of gets annoying to have to do that. So we just sort of say you don't have to do that. We're just going to make our language automatically do that for you. And even for consistency and sort of simplicity in how the language is implemented, everything is quantum even constants. So this is a two-dimensional vector -1, 0. That's a constant value. It's the same in every universe, but behind the scenes, this is still a function from universe to a vector. It just always returns the same vector in every universe. And it just sort of, it works out. It's sort of simpler to think of everything as being the same. And yeah, so this sort of allowed us to design levels in our editor, use tiled, sort of a tile-map editor, and we just type in these expressions into our game, into our editor. And we sort of can program, for example, program this laser to be controlled on the cell. We just type in our quantum expression and it just sort of works. Yeah, so that was pretty much it for the talk. I'm just gonna do some short conclusion. Sort of like I mentioned, we haven't had a lot of time to work on this. We've been working on it on and off for about a year. It's definitely not done. There's a lot more stuff to do. For example, we want to add puzzles with more advanced circuits, teach more circuit identities, teach more quantum algorithms. So we need more puzzles. I could also improve the graphics, improve the user interface, clean up some user interface things, maybe provide like title screen, level select screen, that sort of stuff. The interface is very bare bones. The graphics are sort of mostly temporary. At least the pixel art is sort of just a free tile set that we found. It'd be nice to have our own custom graphics. I don't know, maybe add a story mode. Just like random ideas for what could happen. Yeah, you can, here's the GitHub repository for it. You can download it, play it yourself, play the demo that I showed. And check out the source code. And also, if you are interested in helping us make superposition, you can get in touch with me. Email me if you're interested. We could use, I don't know, programmers, artists, sound designers. Yeah, making a game is a lot of work, so we could use help. So yeah.
I bet there are a lot of people here in chat who would have some great ideas for story and for art and everything. So yeah, please reach out to Sarah on this. I put both the link and your email address in chat.
Cool. Awesome.